Today we are moving towards the next section of section 2, electricity, with the topic of series and parallel circuits over there. Series and parallel circuits. If I talk about the series and parallel circuits, then I can say here that you can connect up circuits in two different ways, in series or in parallel. You need to know the differences between them and be able to work out what sort of circuit should be used in real life applications over there. First of all, we will have to go for series circuits over there. Then I will say here series circuits is basically in series circuit, the different components are connected in a line and end to end. End to end in line means, for example, I am connecting here. This is the resistor 1, this is the resistor 2, this is the resistor 3 over there. And I am joining them end to end over there. And this is my resistor 1, this is my resistor 2, this is my resistor 3 over there. And I am joining with them ammeter over here. I'm joining a voltage supply in the form of a battery over there. And then I will say here that they should get a series there. I'm joining a battery over there with positive and negative terminals. And then I am also joining 3 voltmeters in parallel with them. This is voltmeter for 3. Voltmeter 3 I am connecting at this terminal. Voltmeter at parallel as voltmeter 2. And here I am also adding a voltmeter 1 over here to show the resistance having to be calculated, because in series I know that the current is flowing from positive to negative terminal by passing through this as exactly on this pathway over there. But on the other end, I am also going to describe that voltage is going to divide and current is staying same in this circuit. And between positive and negative terminal of the power supply, except the voltmeters, which is always connected in parallel, but they don't count as part of a circuit. So if you remove or disconnect one component in the circuit is broken, and they all stop working. For example, this resistor 1 is damaged, then resistor 2, even though that is fine, will not work. Resistor 2 and resistor 3 will also not work over there. For a series circuit, there is a bigger supply, which is a potential difference. When more cells are in series to be added, as I have added here only 2 cells over there to make a battery. To make a big potential difference, I will have to use more cells in series. And if they are all connected in the same way, when two batteries of potential difference, like here I say first one is having 1.5 volt, the second one is also 1.5 volt, then the total sum will be 3 volt if I am connecting them in the same pattern as I have connected these two over there. And the current stays the same everywhere, which I will say if it is the I1 current which is entering from this terminal and it is I2 when it is coming out, then current is staying same in the form of I1 is equal to I2 in all the circuit views. Is not dividing in any resistor over there because they are connected in the series over there. So the size of the current depends on the total potential difference and total resistance. And according to Ohm's law, I can say that can be taken as I is equal to V over R. And V is the total potential difference and R is the total resistance of the circuit over there. So I'm also adding the word here total, and I am also adding the word here total over there. In both of these cases, when I am connecting here, then my current is totally depending upon the total resistance and total potential difference, while the potential difference of supply is shared between the components. The potential difference of each component depends on its resistance. For example, the resistance one which I am taking is 10 ohm. Next one is 15 ohm. Next one is 20 ohm. And ohm is the unit of resistance just taken in the form of a little bit omega. This is ohm resistance unit over there. If I am going to define for 1 ohm, if I say 1 ohm is equal to, if 1 volt voltage is provided, then 1 ampere current passes through that circuit, then the resistance will be 1 ohm over there. So in that case, I will say the total resistance of the circuit depends on the number of components and the type of components used for that purpose. So total resistance will be the sum of all the resistances, which I can say like R total will equal to R1 plus R2 plus R3 in that case. So if I want to go for this to be properly calculated, that how these resistances formula is being calculated over there. As I said, in series, current stays the same, but the voltage divides. Then in that case, I will say that voltage divides, then definitely total voltage is V. And I said that is IR1 is the first voltage across resistor 1 plus IR2 is the voltage for across resistor 2 according to Ohm's law, and IR3. Then I can also write it V is equal to V1 plus V2 plus V3 in that case. If I am taking this equation number A over here, then I am saying IR total is equal to IR1 plus IR2 plus IR3. Then in that case, if I take I as common, R1 plus R2 plus R3, then I say here IR total. Then in both of these cases, I is cancelled with I, remaining R total. I am getting exactly the same formula for it, R1 plus R2 plus R3. So this is the way how a resistance of resistors connected in series will be calculated by using this formula over there. After that, I will have to move towards uh, we can say parallel. But before going towards that, I will say in series circuit, it is behaving as all resistor working, otherwise nothing there. And in case of parallel combination, I will say there that parallel combination is going to state its form in the form of everything is independent. Like in your home wiring, the household wirings over there are in parallel circuits over there. Parallel circuits. In parallel circuits, I will simply say here, each component is separately connected to positive and negative terminal of the supply, except ammeter, and always connected in series over there. If you remove or disconnect one component, it will hardly affect the others at all. Like your fan is off, it is not affecting to the light over there. This is obviously how most things must be connected. For example, in cars, and household electronics, each light switch in your house is a part of a branch of parallel circuit. It just turns one light, and on and off are a set of lights over there. And everyday circuits often contain a mixture of series and parallel set parts over there. When looking at components on the same branch, the rules for series circuit apply over there. So for parallel circuit, I will go first. I am going to draw the circuit in parallel combination little bit. I am saying here one resistor is there, second resistor is there, and third resistor is there. They are connected in parallel way. This is a junction with which they are going to connect through a battery. with positive and negative terminals over there. There is a switch. There is an ammeter. And this is a circuit which is given. So R1, R2, R3 are in parallel. So everyone is also having ammeter 1, ammeter 2, and ammeter 3 is added over here. All three ammeters are having the current which is equal to this total current. Ammeter 1 is having current I1, I2, and I3 is there. So I total will equal to I1 plus I2 plus I3. According to this way, I can say current divides and voltage remains the same over there. Like in your household wiring over there, all the shoes are getting 240 volt over there, 220 volt, 230 volt are like that. So the potential difference is the same across all the branches. So I will say V1, V2, V3 in case of R1, R2, R3, V1, V2, V3, everyone is going to equal to V over there. That is V1, which is equal to V2, which is equal to V3 over there. So in this case, I will say here that current is shared between branches and the total current flowing around the circuit is equal to the total of the currents through the separate components, like total is equal to I1 plus I2 plus I3 should be taken into account in case of current division over there. In parallel circuits, there are junctions where the current either splits or rejoins. So this is the point where current splits, and this is the point where it rejoins over there to give you the total current. The total current going into the junction is equal to total current leaving it, and charge cannot just disappear or appear over there. So the current through the branch depends on the resistance of the branch. The higher the resistance, the harder it is for charge to flow. So the lower the current in that branch. For example, you are saying here R1 is 20, R2 is 15, R3 is 10. So the maximum current will flow through R3 over there. Then more or less current is going to flow from R2, and more or less current is going to flow from R1 over there, that is having 20 ohm values as shown in the example over there. On the other hand, if I say if two identical components are connected in parallel, then the same current will flow in each component. For example, you are saying 20, 20, 20. So same current will flow if there is 3 ampere and everyone will get 1 ampere, 1 ampere, 1 ampere. But that will be splitted equally in all three components to be going on over there. And the total resistance overall of the circuit decreases if you add a second resistor in parallel and third resistor in parallel. Definitely its resistance is going to decrease on. And for that purpose, we use the formula. Like as I said, current total is equal to current 1 junction, 1 and 2 and 3 over there. Then for all of these cases, according to Ohm's law, I know that the current is equal to V over R total will equal to V over R1 plus V over R2 plus V over R3. Then I will say here that V is common in all above on both sides over there, and I'm taking common from this right side. Then it is going to cancel out, and I'm getting 1 over R total will equal to 1 over R1 plus 1 over R2 plus 1 over R3 over there. So this is the way how to behave, how to calculate our resistances and our currents to be dealing on, and the voltage staying the same over there. So if I go towards more in detail about this topic, then I will say I will have to move towards charge, voltage, and energy change over there. Now I am moving towards that section where I'm saying here that we should go towards charge. After that, voltage. and energy change. Over there. If I am talking about this, then charge on a positive and negative or negative, that charge can be. And when charge flows, it is called current. Charge can be positive or negative, and when it flows in a wire in a conductor, it is called current. So we can say here that charge through a circuit depends on current and time. According to the formula, Q is equal to I multiply T, which states that I is a current and T is a time. So charge depends on current flowing through a circuit, flowing in a circuit, and the time for which it is flowing. And time for which it is flowing, charge depends upon that. And current is basically rate of charge of flow of electric charge measured in amperes using the ammeter. In solid metal conductors, mostly copper wire, charge is carried by negatively charged electrons. That charge can be negatively charged electrons, which are having their charge as 1.6 multiplied 10 raised to power minus 19 coulomb. This is the electron charge which is flowing through a solid conductor metals over there. When current is flowing there, then we are saying here this formula which I wrote here, Q is equal to I multiply T. I can write it as charge is equal to current multiply time. And by using this relation, I'm also use this triangle form that Q is equal to I multiply T over there. So remember this relation, and more charge passes around a circuit when a bigger current flows through it. When a charge drops through a voltage, it transfers energy. When I take it with the respect to charge flow with respect to voltage over there, then it transfers energy. Here I'm giving a proper statement in as an important point where I say when a charge drops through when a charge drops through a voltage, when a charge drops through a voltage, it transfers energy. So this relation for voltage, when a charge drops through a voltage, it transfers energy. This relation can be explained in the way that energy transfers is equal to, I am saying here, for example, I am saying when an electrical charge is passing through a voltage, the energy E is transferred. Means when a charge, I'm taking the above one, wait. When a charge Q drops through a voltage V, it transfers energy E over there. Okay, energy supplied to the charge at the power source to, we can say, raise it through the voltage, and the charge gives up this energy when it falls through any voltage drop in any component where is the elsewhere in the circuit over there. For example, you are using a electric fan over there in the circuit pathway over there, then charge is going to fall through that voltage which is provided to that fan over there. In that case, energy is supplied to fan for working and throwing the air for yourself. After that, the bigger in the change in voltage, more energy is transferred for a given amount of charge passing through the circuit. This means that a battery with bigger voltage will supply more energy to the circuit for every coulomb charge which flows around it, which I say, like if it is EMF, that is work done per unit charge. If this EMF or voltage of a battery, voltage of battery is providing extra energy, then it is going to provide enough energy for charge to work pass through that component over there. This is because the charge is raised up higher at the start, and more energy will be dissipated in the circuit too. And voltage, basically, if I go for voltage to define over there, voltage is basically, we can say, the energy transferred per unit charged pass, per unit charge passed through that component. Passed through that component, if you want to mention, you can write on. That is called voltage, that is called potential difference, which is measured with the unit of volt over there using an instrument named as voltmeter over there. After that, here I will mention more that the unit of voltage is volt. If 1 joule work is done, 1 joule energy is required, or 1 joule per coulomb, then I can say it is 1 volt. Then it should be taken as 1 joule per coulomb is equal to 1 volt over there. So, and so we can say you can also calculate the energy transferred in joules to or from the amount of charge as it passes through that purpose. Then you will write your energy as a subject. So energy is equal to voltage multiply charge. Multiply charge over there. And that energy will be taken in the form of, we can say, in the form of joules as its main unit over there. But if I take this voltage in the form of V, then according to Ohm's law, V is equal to IR, and I am substituting this, then I am saying energy is equal to I multiply R multiply charge over there. If they are all multiplied, then I am getting the energy value over there. So this is the way how to go for the measurement of energy over there, and how to the calculation of energy should be taken into account. But here I will also mention that when you are going towards energy, then it is directly related to power over there. And if I go for electrical power over there, then as we know in dynamics, we know power is equal to work over time. And if I say P is equal to W over T, and here I'm just multiplying by Q and dividing by Q, so that original equation is not going to be disturbed over there. Then I will say I'm taking the below Q with W over Q dot Q over T. Then work done per unit charge, I know that is voltage, and Q over T, I know that is current. So P is equal to VI. VI. This is called electrical power having unit watt over there. In the same way, when we are taking power is having unit watt, then using this V in the form of IR, then I am saying P is equal to IR into I, can also be written as I square R. So this is also the power formula. If I replace this I with V by R, then P is equal to V by R into this I is replaced by V by R into V, then it is V square by R. So these three formulas can be used for calculation of electrical power through any component giving upon the data which is provided to you. You can use these electrical power formula over there. And this electrical power formula can also be used to measure the energy over there. As I said, that power is equal to work over time. So work is energy. So power multiplied time. If you are taking your power VI, then you can saying VIT will also give you the energy. I square RT will also give you the energy. RT and V square over R into T will also give you the energy in the form of electrical energy. And if I want to show here that it will use kilowatt hour as its unit for electrical energy, that is kilowatt hour, which is having kilo is 1000, hour is 3600, so it is 3.6 mega joules, which is used for 1 kilowatt hour as electrical energy formula over there. So tomorrow, inshallah, in the next class, we will visit towards the electrical safety equipments, and we will also go towards electric current to pass through them of resistor, and we will move towards static electricity, and it's a little bit examples. Then this section number 2 will be finished, and try to be focused and working with the proper revision of your topics. It will be much helpful for the preparation of your final exams. Thank you so much for today's video. Kindly subscribe my channel and share the video, like the video. And if you find any concept not clearly explained there, kindly contact via comment or in my video description or in channel description. There is given the WhatsApp number. You can also contact through that. Thank you so much. Allah Hafiz.